In this video, we're going to go through ionic solids. Ionic solids consist of positive cations and negative anions, so a metal and a nonmetal. Ionic solids are non-volatile, meaning essentially non-reacting, and have high melting points. It takes a lot of energy to separate these because of such a strong attraction between the cations and the anions. As solids, they do not conduct electricity. When you melt an ionic solid or dissolve it in solution, they do conduct electricity. It frees up the ions and they're able to move, and electricity is able to be conducted. Many ionic compounds are soluble in polar solvents and insoluble in nonpolar solvents. Okay, let me explain why. So, water. Water is a polar solvent. Okay, so we've got our oxygen, we have hydrogens, right? So hydrogen is a positive, and oxygen is going to be negative, and then NaCl. Okay, so we've got sodium. So this will be positive, and this will be negative. So our positives will attract to the negatives, and then the negatives will attract to the positives. So what's going to happen if you throw table salt, NaCl, into water, H2O, the positive and negative will attract and it will essentially shred your ionic compound. So the positives will rip apart from the negatives, and you will have sodium being attracted to the oxygens and then chlorine being attracted to the hydrogens, and it will rip apart your ionic molecule. Okay, so it will dissolve it in solution. Alright, so an ionic solid looks like this. So you've got a cation and an anion. Cations are positive, anions are negative, and they will form a crystalline structure that repeats. So positive, negative, positive, negative, positive, negative. So if you have a large quantity of ionic solids, they're going to arrange themselves. So it'll look like this. Kind of a chain that repeats. Okay, so here's one molecule, here's another, and it just kind of repeats in this order. And also you've got attraction going on here, and here, and here, and here. So very strong, held together with the charges. So positive, negative, just repeats, and they all hold each other together. So let's look at an example. It says, draw a particle diagram of sodium chloride. We kind of already did that with the letters, but let's do it with the charges. So again, it will be positive, negative. So you'll have your attraction here. And then here would be the next one, positive, negative. So it just essentially repeats in this process. So if you have a particle diagram where it's repeating positive, negative, that's an ionic solid. And obviously these would be much closer together, but I wanted to separate them a little bit so you could tell the difference between the particles. Okay, so particle diagram, ionic solid should just repeat positive, negative. All right, which of the following would represent an ionic solid, and what is wrong with the others? So should easily be able to tell that this is an ionic solid. So it repeats in the order positive, negative. If you look here, this one repeats in the order positive, negative. However, if you notice vertically, you have two positives together, two negatives together, so this one wouldn't work. Here, these are too far together, so they need to be closely spaced like this when you're drawing them together. So this one wouldn't work. So again, both horizontally and vertically, they need to repeat positive, negative, and then vertically positive, negative. The ionic solids repeat in that way. Why does potassium bromide have a higher lattice energy than potassium iodide? Well, let's look at our periodic table and let's see where they are. So we have potassium bromide. So potassium and then bromide is way on the other side. So actually they're in the same period number 4, and potassium iodide. So we have potassium here, but if you notice, iodine is one period down, so it has a larger radius. So both potassium and bromine have 3 rings or shells. Iodine, though, has 4. Oh, did not draw that one very circular. There we go. So it's going to be much bigger. So the lattice energy between potassium and iodine is lower because your valence electrons are a lot further away. There is less of an attraction between the nucleus and those valence electrons. Whereas both potassium and bromine, you have a shorter distance between the nucleus and the valence electrons. So in the case of potassium and bromine, you need more energy to transfer electrons from the cation to the anion, because in the case of potassium, there is a much stronger attraction to the nucleus, whereas in iodine, there is a much greater distance from the nucleus to the valence electrons. So more distance is going to result in a weaker attraction.